Okay guys, as promised, we're going to start this video out working these two problems. This, the first problem's a little more difficult than the second problem, but second problem is one that I expect you to be getting pretty good at by now. So let's get to it. So it says at a break-even point of 500 units sold, the variable costs were 125 and the fixed costs were 10,000. What will the 501st unit sold contribute to profit? So guys, at the long and short of it, we're going to need a cost function. We're going to need a revenue function. And we're going to need a profit function. Okay? Cost function is going to be really easy because we have our fixed cost and our variable cost provided. So we know that the marginal cost, the variable cost, again, this is marginal. I said this in an earlier video, but it maybe didn't stick, that variable cost and marginal cost is saying the same thing. So I know the 125x is the variable or marginal cost, and the fixed cost is 10,000. Now, what kicks in next is this quantity being 500 being the break-even point. Well, that tells me that my revenue at 500 is equal to my cost at 500. I don't know my revenue function, but I know my cost function is 125 x plus 10,000. So therefore I know that the revenue at 500 has to be this value put into my cost function. All right, so I'm going to use my calculator here. So we get 72,500. And I know my revenue function is the price times the quantity. So 72,500 divided by 500. I know that this product was sold at $145. Now, if you think about it, what we've got here is we've got something sold at $145 per unit, and we've got something that cost $125 per unit. So if you think about it, you're making, because the fixed cost is held stable, it's held constant. So you're making that when the product is sold at $145 and the variable cost per unit is $125, then you know that the difference, $20, has to be the amount. Let me get that down there where you can see it. Has to be the difference in 145 and 125 has to be the amount of profit that goes for the additional unit. So you really don't have to do much else for 501. I'm sorry, from 500 to 501, or 199 to 200, or 350 to 351st. Whenever you increase that 1 unit, the profit will be the difference between the cost per unit and the revenue per unit. So that turns out to be pretty easy. Now, the next problem, problem number 2, I'm going to give you kind of the gist of it. So I'll tell you what, let me put this up here where you guys can see that. Okay. So number 2 says a producer of DVDs is producing an instructional DVD. She estimates it will cost $90,000 to record the DVD and $5.10 per unit to copy and distribute it. If the wholesale price is $14.70, so we're looking at this by wholesale price. We're looking at this at the supplier. So they're going to sell a DVD to someone, and we don't know how much they're going to sell it. Well, we know they're going to sell it to them for $14.70. We don't know how much the retailer is going to sell it for, but that turns out to be actually irrelevant in this situation. So, gang, this is a really, really easy problem. We know that our cost is going to be 510x plus the fixed cost. Cost them $90,000 to get started. And they're selling this thing. It's technically, I wouldn't think it's the retail, the retail, but it still is the revenue for this company at $14.70 per unit. Okay. Well, guys, revenue is when the cost. I'm sorry, not revenue. Break even is when the cost equal the revenue. So subtract 510 from both sides. Divide both sides by $9.60. And we get 9,375 units. So they're going to have to produce a whole lot of DVDs to be able to break even. All right, gang. New stuff we got going on here. The exponential functions. We're going to need exponential functions for the following reason. We're going to eventually, once we get into the mathematics of finance for this class, which is actually the fun part, we're going to see that our ending balance of an investment can be found by taking the principal, which is the original investment, times 1 plus r over n raised to the nt power. Now, r turns out to be our rate, 6%, 5%, 2%, whatever it may be. N turns out to be the number of times that we compound the money per year. When we borrow money, we usually compound things 12 times a year because we usually make monthly payments. But it doesn't have to be that way. And then you'll notice that in the exponent we have variables too. We have n, the number of times something is compounded, times t, the number of years that the investment is actually, the number of years the investment or the amount of the principal has been invested. Easy for you to say. So we could say that if we, for example, invest $10,000, at an interest rate of 3%, compounded quarterly for 20 years, then we could very, very, very easily find the value of our investment. So now I like to work things inside out here. So I would go ahead and do the 0.03 divided by 4 because I'm weird. And I like to get the right answer. Then I would add 1. And then I would raise that to the 4 times 20 power. Now, are there easier ways to do this? Absolutely. And I'm going to teach you how to do that as we go on. But, we're kind of crawling right now. So I want to raise that there, okay? And then I want to multiply by the initial investment. And guys, 20 years from now, if you get 3% on your money for an investment of $10,000 compounded quarterly, you're going to end up with $18,180.44. Now, the motivation for this is to realize that some functions that we run into have the variable in the exponent. So when the variable is in the exponent, we call this an exponential function. All right? Now, I want to start this kind of simple, and then we're going to get to the to the goal of this video. But I just want to tell you a few properties of exponential functions. So if we have, say, f of x is just b to the x power, and we're going to keep our b's greater than 0, and we're also going to not have the redundant case where b is not equal to 1. So got some basic properties that these functions take on. First of all, they will all pass through the point 0, 1. So when I go over here to look at the graph of one of these things, I know that this graph is going to pass through that point. Second thing we know is these are continuous functions. In other words, there's no breaks, there's no holes, there's no jumping. The x-axis is running out of room here. Serves as an asymptote. Now, an asymptote means that it's a line that the graph gets closer and closer to. So let me just jump up here. Let's say that we have a graph where like x equal 2 is a vertical asymptote. Well, that would just tell us that this graph would get closer and closer and closer to that line, but it would never touch it. Well, these graphs right here get closer and closer and closer to the x-axis, but they never touch it. Okay? Another important property, when b is greater than 1, then we have an increasing function. And when b is between 0 and 1, then we have a decreasing function. I think this is going to be handled pretty nicely using the calculator. Okay, so let's just take a look at a graph here. So let's go in y equals, and let's clear this out, and let's choose some b greater than 1. Let's just look at, for example, 3. Now, to create an exponential function, we have to use this button right here, this caret key, if you will. So that allows us to come in with an exponent, and I want to come in with x, so that will give me that function. Now I'd like to come in and do something like this, but where b is between 0 and 1. So this one I'm just going to do a half and raise it to the x power. Now I have just a generic function here, nothing that takes on any particular value. Well, not particular. It takes on numeric values, but it's not. We're not dealing with money. We're not dealing with cherries and stuff like we did before. But what I can do in that situation is I can just go zoom and go zoom standard, which is number 6, and that will give me just a x axis from -10 to +10 and y-axis from -10 to +10. Now you can see that these things don't go below, they don't have negative y values. So I could get a better picture by coming down and just putting y at 0, because I'm never going to go below the x-axis. So guys, what happens here is the first function. This one right here is the 3 raised to the x power. Notice as it goes to the left, it gets closer and closer and closer, so it increases, as I told you. And this function decreases, and it gets closer and closer and closer to the x-axis as x gets larger. So whether or not this thing is increasing or decreasing depends on the b value that we actually have. Now, the kinds of functions that I want you to look at, now if you think about it, this is kind of my b raised to the x power up here. This whole thing here just turns out to be our b, and this nt turns out to be our x. But notice we have a value in front, which is p, which leads me into another form of exponential functions. In its simplest case. Now, again, just depending on whether or not we want to use standard notation or function notation, and from here on, once we get into big boy, big girl stuff, we typically concentrate on function notation. All right? So let's say, for example, I don't know. What are we going to do here? Let's say we have the following values. I'm trying to come up with something kind of here on the fly. Let's say that we have the point 1, 2. And we have the point 3, 192. And the goal here is to find the function that fits that passes through these 2 points, and you can kind of see that this is going to go up quite fast. For example, if I have 112, it's going to be there someplace, and of course, if I have 2, 192, it's going to be way up here. So you can see where this thing, knowing it comes to 0, 1, it's going to increase very, very quickly, and has the natural tendency or the natural properties of an exponential function. So, guys, I'm going to show you how I would work this. The first thing I would do always in working, coming up with the equation of an exponential function, is I would start with the big numbers. Okay, so I would know that from 3, 192, that when I have the form y equals a times b raised to the x power, that my y is a times b raised to the 3rd power. And again, where in the world does this come from? Well, it comes from this part right here. It comes from y equals a times bx. When I have 3, 192, my x is 3, my y is 192, and I've just put that in there. Okay? Next thing I'm going to do is I'm going to look at my next number, which is 112. So what do I know here? I know that my y is 12. I don't know my a, I don't know my b, but I know b to the 1st power gives me, b to the 1st power. All right. Now what I'm going to do is I'm going to do some trickery, and I'm going to divide both sides and create this. Now, can I do that? Absolutely. If I have 2 things that are equal to each other, I could add these sides over here, I can subtract these sides over here, I can multiply these sides over here, or in this case I can divide these sides over here. So guys, I have 192 divided by 12, which is 16. These A's will cancel. And guys, remember a property that b to the m over b to the n is equal to b to the m minus n. So I'm going to take 3 over 1, 3 and 1, so I subtract those. And I get b squared. Okay? Now, what I want to do next, I would take the square root of both sides, but I want to show you something that's more general than that. What I would like to do now is I would like to raise both of these powers, both these sides, to the 1/2 power. Now, granted, I could have taken the square root, but what happens in the next problem if you get like b to the 5th over b squared? Now, you're going to need something more general than just a square root. So if we raise something to the multiplicative inverse, because remember there's another property that says b to the m raised to the nth power, we just multiply these powers. So over here I'm going to have 16 to the 1/2 power equals b to the 2 times 1 power, which is just b to the 1st power. So guys, from all this, I know that b has to be 16 to the 1/2 power. I can use my calculator. To the 1/2 power, you probably know what the answer is, so the b is going to be equal to 4. Now, what I can do now is I can take one of my relationships. For example, I usually like to work with the smaller one here. So I know that 12 is equal to a times b raised to the 1st power. But I know that b has to be equal to 4. If I divide both sides by 4, I know that a has to be equal to 3. So guys, take in consideration that I know my b is equal to 4. I know my a is equal to 3. I have, back to the form of y equals a times bx. I have my function is y equal 3 times 4 raised to the x power. Now I always like to come in and check things out and make sure that, that everything's working as it should. So what I could do here is I can come into y equals, and I can have 3 times 4 raised to the x power. I can think about my window, and my x's in this problem ran from 0 to, from 1 to 3, so I'm going to go just 0 to 5. And my y's went from 12 to 192, so I'm going to start this at 0 and go up to about 250 or so. So I can get my exponential function here. Now I can use the calculator to check to see if my answer is plausible. Now, again, right here, there's a calculator key called calc. So if I go calc, last time I went there, I did it to get the intersection, but now I can actually take a function that I have in my calculator and use value. So value is 1. So when x is 1, I better get 12, right? And I did. And when x is 3, I better get 192. So guys, I'm fully invested that I have the function that actually fits what I need. Now, let's see if we can actually can make this apply. Let's take the following scenario, or let's just call it a situation. So kind of a financial situation. We know that 2 years after an investment, we have $12,500. 25 years after an investment, we have $72,500. Let's find the exponential model. And see what this exponential model tells us about this investment. All right, so what I want to do here is let's put the stuff that I know. I know that 2 years later, we have 12,500. 25 years later, we have 72,500. You know that Darbro told you to start with the biggest number. And then put the smaller number below it. Darbro next told you to divide both sides to create this. The A's will cancel. 72,500 divided by 12,500 gives me 5.8. And what's going to happen with our b's? This will be b to the 23rd power. So gang, I have 5.8 equals b to the 23rd power. Now if I tried to take the square root, it doesn't work, but using the trick that I told you guys, I can see that b is equal to (5.8) raised to the 1 over the 23 power. Now guys, it's going to be tempting for some of you not to put that parentheses there. And let me show you what happens if you don't do that. Well, if you put 5.8 raised to the 1 divided by 23, what that'll do is that'll take 5.8 and raise it to the first power and calculate that, and it'll take that answer and divide by 23. That's not what you want. You want 5.8 raised to the entire. So gang, what we end up with there is a b value. I'm going to call it 1.0 0.079. Okay. Now, just like I did before, I'm going to choose one of these ordered pairs. I usually choose the smallest now, only because smaller numbers are equal, just easier to deal with. So I know that my smaller one, when I have a y of 12,500, I don't know my a value. I know my b is 1.079. And I know that the x value is 2. So guys, I can take 12,500 divided by 1.079 raised to the second power. And I can see that my a is equal to 10,736.61. So putting everything together, I know that my value, y, can be the a value, 10,730, I'm just going to do 10,737 times my b, raised to the x power. What I may want to look at this is the value in terms of time. T years after the investment is made. Now, if we go back to the original ending balance was P times 1 plus R over N raised to the NT power, what we've assumed here is that our money was invested one time per year. So this is going to be P times 1 plus our rate raised to the T power. So what can I determine from all this? I can determine P as my beginning balance. From this, I can see that the investment was $10,737. Since 1 plus R is in here, I know that my rate, what was added, what was the rate here? 0.079. So that tells me that these people invested $10,737 and got 7.9% on their investment. All right? So isn't this fun? Okay. Let's try another one. May not be so fun. But actually it is. I think it's actually kind of cool. So let's say, for example, that let's just go just kind of a generic XY, and let's say that in the year 1994 we have something, whatever we're measuring, was 2.4, and let's say in 2000 that we know it's 72.4. Now, what I would do here is I would think about this as time, and I don't know what this stands for, but this is some sort of amount as a function of time. And what I may want to do, and what we often do in these problems, is I may want to let this be 0 and let this be 6, because let this be my starting time, and let this be the number of years after the starting time. Now, I couldn't do that with my investment because the previous problem, Now, and I always try to change things up for you because that's where learning actually comes in, when you see a problem in one form, but then you work the next problem and something's changed a little bit. How do we adapt to that? Well, to me, that's learning. That's when you know what you're doing, when you can adapt. So we're adapting a little bit from the previous problem in that we've got some flexibility, that we've got a beginning time, and we want to create the exponential function that connects these 2 points. So guys, the way I would look at this is I would look at it as 0, 2.4, and I would look at it as 6, 72.4. So again, what would Darbro tell you? Start with the biggest. So 72.4 equals a times b to the 6th power. And then I would look at 2.4 equals a times b raised to the 0 power. All right, divide both sides. So 72.4 divided by 2.4 is 30.166666. So I'm going to go out, say 3 places. That should give me pretty decent technical accuracy. And over here I get b to the 6th power. Guys, raise both sides. I'll tell you what I'm going to do. I'm going to go out 4 places because I know that actually gives me so guys, my b in this situation is going to be 30.166666. And of course, without question, the best way to do that is just keep the entire decimal expansion in your calculator and just raise it to the 1/6 power. This is by far the most efficient way to give you the best answer. So guys, we're going to get 1.76 as our b. And our a is going to turn out to be really cool because if I take my smallest, which is the 0, 2.4, I can see that my y is 2.4, my a I don't know, my b is 1.76, and my x is 0. Well guys, anything raised to the 0 power is equal to 1. So guys, my a would be 2.4. So kind of got lucky here, so y is going to be 2.4 times 1.76 raised to the x power. Check it out, because we want to make sure we get questions correct. I'll tell you what I'm going to do. I'm going to go back to this one. I think it shows up a little better. So gang, go to, let's get rid of some stuff here. We're not doing supply demand anymore. So let's do 2.4 raised to 1.76 raised to the x power. All right. Choose a reasonable window. Well, we don't want x's up around 9,500 and 16,500 because we actually dealt with from 0 to 10. Actually 0 to 6. And our y's were in the 2 and 72 range, so I'm going to go from 0. I'm just going to allow some room for error, room for growth, go up to 200. Exponential functions grow very quickly, kind of like something grows exponentially. It means that it starts out slow and grows as we get bigger. So let's go calc and try out our 0. Should get something close to 2.4. We did. And go calc again. And let's put in 6. and we should get something close to 72.4, which is actually off a little bit. And that's not cool, but what happened is we rounded that 1.76 to two places, and if we had rounded it further out, we would have got a much better answer. So, gang, all I got for you in terms of exponential functions. So there's one of these on your my math lab assignment this week. So I may put up another video just on exponential functions here. Maybe just work a couple of extra problems, but then I may not. Just depends on how the week goes. So, gang, have a good one.